All right, we'll get started. In the folder for this week, let me get to it here. Got a couple other people coming in too. Okay, on the right-hand side of the course, you'll see the this thing says determining solubility assignment. That's a thing that's like a check about stuff I want to show you about today. And then there's that activity series lab, which I showed you how to do yesterday, but I'm not going to talk for a whole long time today here now. I'll take questions about the lab if you have questions about the lab or you have trouble with anything at all. But if you weren't in yesterday, the activity series lab, the information for that is whenever you're in Unit 6, current unit, in the thing for this week. There's the lab itself, along with the videos that go with it. So you're going to have to watch those videos to be able to see what happens with the reaction, to relate that to the data table that exists in the activity series lab. The other things you'll find in the folder, hold on, let me check something here. I guess we're good. The other things that you'll see in the folder, there's this thing that says solubility notes. So this is a PDF of slides from a PowerPoint thing that I'll show you about today about the solubility chart and how solubility rules work. So that's here for your reference. It's only a couple pages long, but there's more examples that'll be that I'll show you here in class, and of course it's in the video too. This other thing says solubility chart. This solubility chart is on the back side of the activity series. So I passed out like an activity series on paper if you were in school, and on the back of it there's this chart that says solubility chart. And I know it's all kind of small and whatnot, but there's a lot of information that has to get packed in onto it. I'm going to reference this today. So that solubilities chart is another tool that you need to have handy. And this determining solubility assignment, this you need to get done today, but you'll have time at the end of class to use the solubility chart to determine whether or not something is actually soluble. And I'll tell you what that means here today anyway. Okay, so let me show you some stuff real quick, and then I'll take questions about things. In that slide deck about predicting solubility. Okay, so what it means to be soluble is that something can form a solution in water. That SOL doesn't refer to, when we say a solution, we're not talking about like an answer to, like in math, you might have an answer, which is a solution to a problem. When we say solution in chemistry, what we're talking about is something that is dissolved in water. And that dissolve, the word dissolve has SOL in it as well. So anytime you see SOL, that refers to being in water or being part of water, whether you say dissolved or it's a solution of. If something is soluble in water, it dissolves in the water. It's not a solid in water. So like the most basic idea is if you were to take a little bit of salt, sodium chloride, mix it in with water, the sodium chloride ends up in solution. The salt doesn't settle to the bottom. Instead, it becomes part of the water. So like the ocean is full of salt, but it isn't salt sitting on the bottom of the ocean. It's salt that's in the water column itself. And in the lab, these solutions of different substances may just look like pure clean water, except it's not. So the water that comes in through pipes into your tap into your home, that's a solution. There's stuff that's in that water. Some things intentionally, some things unintentionally. There's some sodium, there's some chlorine, there's some calcium. We intentionally put chlorine in the water in order to kill, any kind of bacteria or viruses that are in the water. We also intentionally put fluorine in water because fluorine helps make your teeth stronger as the fluoride ion. So there are some words that go together, and they're not exactly synonyms for each other, but they're used in different contexts in chemistry. What is dissolving? What it means to dissolve. Ionic compounds are compounds that form between positive and negative ions, and generically, ionic compounds are called salts. So when you hear the word salt, you probably just think of regular salt like salt and pepper, and that salt is sodium chloride, but that's only one example of a salt. Anything that is an ionic compound is a salt. So if you say to a chemist, hey, do you have some salt? Instantly they're like, well, there's hundreds of salts. And they're not just being a jerk about it. They're just saying that salt just means any ionic compound. So usually sodium chloride in chemistry, we call that table salt because that's the kind of salt you know have in a salt shaker on a table. Whenever you put a salt or an ionic compound that is soluble in water, it dissolves in the water. And that concept of dissolving means that if you have that ionic compound like nitrate, calcium nitrate is soluble in water. So what this shows is you have solid calcium nitrate, like calcium nitrate crystals, just the same as if you have salt in a salt shaker, that's solid sodium chloride. And a simple dissociation, which isn't exactly a chemical reaction, but can be written as a chemical reaction, is if you take calcium nitrate, which is a solid, and put it into water, what happens is it dissociates. The individual ions of calcium and nitrate separate and end up kind of floating around in the water itself. A more simple example is, here's like a container and it has some water in it, and we have some salt crystals. So you might have a crystal of salt, which is also called halide. You got NaCl. And NaCl is a solid crystal of salt. The sodium and the chlorine ions are bonded to each other and it makes a solid. But when you put that sodium chloride crystal into the water, it's no longer exactly sodium chloride. It's no longer a compound. Instead, you have separate sodium ions and chlorine ions, and they're all over the place in solution. They're completely dissociated from each other. And what it means to be dissociated is like the opposite of being associated. Like if you're associated with something, you're aligned with it, or you're close to it, or you're part of it. So being associated means that you're together. Being dissociated means that you're apart or you're separate in some kind of way. So if solid sodium chloride is put into water, it dissociates. And then, in a way, you can write it a couple different ways. But really, NaCl as a solid, when it's put into water, becomes sodium ions, which are aqueous, and chlorine ions, which are aqueous, chloride ions. But generally, the way we write it in a chemical equation is to say that there's sodium and chlorine in water. We just usually write NaCl AQ. So whenever you put the AQ after a chemical that is soluble in water, that tells you not that there are sodium chloride crystals or the sodium and the chlorine are associated with each other, but instead NaCl AQ means that there's sodium chloride that you would put into water. The ratio of sodium to chlorine is 1-to-1 in the water, but they exist as individual ions. So really this Na plus aqueous plus Cl minus aqueous is kind of synonymous with writing NaCl AQ. So what it means to be aqueous is that the substance was a compound, but now it's in water, and the ions are dissociated from each other, and they just kind of exist separately in the water itself. So there are all these words: dissolve, dissociate, ionic compound, salt, aqueous, and those words are all associated with each other, or they're all related to each other in the sense that you got some solid thing that went into water, it broke up into the ions, and those ions exist separately. So that's really the meaning of being aqueous. Now, without the water, all those ions are going to reassociate with each other. So if you've got salt water and then the water evaporates. And when water evaporates and goes into the air, it leaves the salt behind, and the salt will end up, being like crusty, and you end up with salt crystals once again. So those individual ions will reassociate with each other. Now, not all ionic compounds, when you put them into water, do they dissociate. There are ionic compounds, and lots of them, that when you put them into water, they remain um, as those solid ionic compounds. So, how do you tell the difference between whether something is going to dissolve or not, or whether it's a solid or not? And in a number of reactions that we did last week, you mix some things together, saw chemical reactions take place, and as a result, you ended up with solid. So one way that you can see that a chemical reaction takes place is that it's a change in phase. So sometimes you mix two things that are soluble in water with each other, and a solid forms. And the reason why the solid forms is because something new has been created that is no longer aqueous. This process is mostly related to double displacement reactions or double replacement reactions. It doesn't matter if you call them double displacement or double replacement. They really mean the same thing. So either double displacement or double replacement reaction. We have solubility rules, and those rules are not man-made rules. Those rules are like laws of nature. They are uh, determined based upon not anything humans have done, but based upon what we observe, how different chemicals behave in water. And after the chemical, we put these state symbols. So we call them states or we call them phases, but whether you write NaClAq or NaCl solid tells you whether or not the stuff happens to be in water, or for some ionic compounds in water, they remain as a solid. So this AQ or this S, those are the state symbols. Uh, solid or liquid also refer to phases, but aqueous isn't really a phase or a state in terms of being solid, liquid, or gas. But aqueous tells you that something that was solid, that's now in water, has already dissociated. All right, when a solid forms, those solids are called precipitates. People pronounce it precipitate or precipitate, but a precipitate is a solid that forms whenever you put ionic compounds together and there's some new solid that's made. We put an S as a state symbol, you see a solid that forms. You've already seen it. I'm going to show you a good example of precipitates. So the best example that you saw last week, you did a lab and you mixed some silver nitrate and calcium chloride together. And if you were, let me change to a different screen. If you were remote, then you watch this as a video. But if you were in person, then you saw this live. So what these two chemicals was this one has silver nitrate in it, and the silver nitrate in this water is a solution. So there's silver ions and nitrate ions that are separate ions, and this solution is an aqueous solution. And then there was calcium chloride. And calcium chloride, those ions have become separated as well. So you have a solution of aqueous silver nitrate and a solution of aqueous calcium chloride. And then whenever in this experiment I poured the calcium chloride into the silver nitrate, and whenever that's poured in there, all of a sudden it doesn't look like a clear and colorless solution anymore. Instead, it looked like super milky. And this actually isn't still a solution. Instead, you've formed very small crystals, but they just haven't quite settled out yet. So if you were to wait, this solution settles out and you end up with solids at the bottom, and it's nice and clear at the top. But because you form these ions as very tiny crystals, and this one also like got a little bit cool, it was endothermic. One of those, what's in that water that's a solid, we can now predict what that solid was. So let me show you how to do that. This ion chart, or this is a solubility chart, and this solubility chart has columns and rows. And the way that it's organized is the vertical columns. If you see what's true about all those things, they'll have positive charges after them. So these are the cations going down the vertical side. And the thing I'll need to note, it says group 1 plus NH4. Group 1 elements, those are the alkali metals. So the alkali metals are all of these. So when it says group 1 elements, that refers to everything in this column: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. In addition to that, there's the ammonium ion. So anything that's in group 1 plus the ammonium ion, that's all in this row. But then there's other things: aluminum 3, barium 2, bismuth 3, calcium 2, so on and so forth. The columns are for anions. So this is the acetate, like C2H3O2, that's acetate for like, vinegar is hydrogen acetate. Um, this is the arsenide, bromide, carbonate, and so on and so forth. Many of these are polyatomic ions, but they all have negative charges going across the top. So how this works is, in that reaction, we had silver nitrate. And how you deal with silver nitrate to find out if it's soluble is you go and find silver. So here's silver on the horizontal rows, and then you go and find nitrate, and that's in this vertical column. And where silver and nitrate come together, you see it says AQ. So that was aqueous silver nitrate, AgNO3 AQ. You don't even need to see the ion chart to know that, because the silver nitrate in solution looked like a clear and colorless bit of water. It looked like only water, but really what was in that water was separate silver ions and nitrate ions. And then also calcium chloride. So calcium chloride, here's calcium, and there's chloride. So when you go from calcium chloride, that also says aqueous, AQ. So you had silver nitrate plus calcium chloride. Calcium chloride is going to be CaCl2, and that's because calcium has a charge of 2, chlorine has a charge of 1. Now, this is a double replacement reaction, or double displacement reaction. So what happens in a double replacement reaction, possibly, is that the cations switch places. The silver goes with the chlorine, and the calcium goes with the nitrate. So the products that you would predict that would form would be silver chloride, and silver has a charge of 1, AgCl, so it's just AgCl, and then calcium nitrate, CaNO3 2. And this equation is not balanced. We can balance the equation. So you're going to need like a 2 in front of the silver, and then let's see, 2 in front of the silver nitrate. So that balances the equation. 2 silver nitrates and 1 calcium chloride make 2 silver chlorides and 1 calcium nitrate. So now the question is this: that white stuff that formed in the water, is that silver chloride, or is that calcium nitrate? Or could it be that both of these things are solids? So here's what you do. This is all you have to do. The silver chloride is now silver with the chlorine. And so when I go silver and chlorine, you see that says S. But then the calcium nitrate, calcium and nitrate, that says AQ. So the stuff that's in the water that's white is silver chloride, because on the solubility chart, silver and chlorine, it's got an S. This is the solid. Silver chloride is a solid, and therefore this silver chloride, that's the precipitate. And often the precipitate is white. It could be a different color. It could be yellow, could be blue, could be green. typically is white. Most ionic compounds are white in color. That's the white substance that is going to settle out in solution. The calcium nitrate, the calcium and nitrate, that says AQ. So that actually remains in solution. So what you end up with in that container or in that beaker is when we're all done, and if it settles out, there's going to be solid, I'll just have yellow because white doesn't make any sense. There's solid silver chloride sitting in the bottom, but this calcium nitrate, those are still calcium ions kind of all floating around, and nitrate anions, they're all over the place. Really doesn't matter where I draw them. There's billions of them, just unbelievable numbers of them in that solution. So silver chloride settles down to the bottom. Calcium nitrate, the calcium and the nitrate anions, aqueous means that they stay in solution. So that's what you saw, and that's how to predict which one is which. Because you could say, well, I don't know which one is settled out. It's also possible that when you react these two things, you make two things that stay solid. So it could be that you end up with two reactants that are aqueous and then two products that are solid, and the reaction goes. So that's one example. Okay, here's another example. We got sodium hydroxide and iron 3 chloride. These are both aqueous, so these are both substances that when in the water are separate ions, sodium ions and hydroxide ions, iron ions and chloride ions. We form two things, sodium chloride and iron hydroxide. You can see here what happens is the sodium replaces the iron and the iron replaces the sodium. So instead of it being sodium with hydroxide, sodium goes with the chloride. Instead of it being iron with the chloride, or iron with the chloride, iron goes with the hydroxide. One of these two things is the precipitate. So all you got to do is for NaCl, you just find a solubility chart. Now, Na, if you look on this list, you don't find Na. There's no Na on the list. But the deal is sodium is one of the group 1 elements. Because sodium is a group 1 element on the solubility chart, that's kind of like in this thing. Hold on, let me slide this over. There we go. Sodium is in here. Sodium is in group 1. And the thing you'll notice about group 1 elements, they are all aqueous, no matter what. Sodium, anything is aqueous. You also notice other things. Hydroxides are generally solids. There are a couple hydroxides which are aqueous, like group 1 hydroxides, barium hydroxide, but lots of other hydroxides are insoluble. They form solids. So sodium hydroxide is one. Sodium hydroxide is aqueous. So this thing, aqueous. But then iron hydroxide, and this must be iron 3. And you know that because hydroxide is OH minus, and it must be iron 3 because there are 3 hydroxides. So iron 3 hydroxide, iron 3 is right here. When you go iron 3 hydroxide, that says S. S stands for solid, doesn't stand for soluble, stands for solid. So iron 3 hydroxide has solid. That's the precipitate. So whenever sodium hydroxide and iron 3 chloride are mixed together, you end up with sodium and chloride ions in solution, but iron hydroxide settles out to the bottom. So as a result of the reaction, you've got like solid iron hydroxide down here. And there's different ways to separate that. You can put it in a centrifuge and spin it around. That'll separate. Sometimes you can just wait and it'll settle down. You can also separate it by filtration. You can get some filter paper, run the solution through the filter paper, and the solid will get caught by the filter paper. We'll work on those techniques later on in the course. But the iron hydroxide settles to the bottom, and the sodium chloride, those are still just sodium ions, separately kind of chilling in the water, and chloride ions, Cl minus, And they're a 1-to-1 ratio. We don't know how many there are. There's going to be a lot of them. But the sodium and the chloride ions stay up in solution. You don't see a color. The ions themselves are in a way are invisible, but the iron hydroxide, that settles down to the bottom. So that's the kind of thing you have to do. So another example, this is in the slides. Silver nitrate, sodium bromide does a precipitate form. So you can write silver nitrate and sodium bromide, and what you would predict is that the silver goes with the bromide and the sodium goes with the nitrate. So the products you'd expect are sodium nitrate and silver bromide. And it turns out they all have a charge of 1, so that's easy to write the equations. There's no other subscripts, because silver has a charge of 1, bromine has a charge of -1, sodium's +1, nitrate is -1. So these two things, we can look to see, were they solids or were they aqueous to start with? The silver nitrate, on the ion chart, silver is here and nitrate is here. So silver nitrate, that says aqueous. So you can put an AQ. The sodium bromide, sodium is in group 1. Sodium bromide is also aqueous. So sodium bromide is aqueous. Now, sodium nitrate. So what's up with the sodium nitrate? Is sodium nitrate soluble? Is there an AQ in the chart for sodium nitrate? So sodium is a group 1 element, and sodium nitrate is right here. So sodium's group 1 under nitrate. It says AQ. So this is aqueous. And then silver bromide. So silver is right here, and you go to bromide, silver bromide says solid. So when this reaction takes place, silver bromide is solid. You start out with 2 solutions, silver nitrate and sodium bromide, and as a result, just like we showed you with the other one, you end up with silver bromide down in the bottom. So this is going to be the solid, AgBr solid, and then you have sodium nitrate. So you got some sodium ions and some nitrates, NO3 minus. Those stay in solution. Some solutions do have a color, like a lot of copper solutions are blue or green, but they're always like transparent, usually always transparent. They're easy to see through. It's actually the copper ions in solution that give it a little bit of color. All right, so other ones, sulfuric acid, barium chloride. You should be good at writing equations for chemicals now. Sulfuric acid came from sulfate. So sulfuric acid, acids are always H plus, and sulfuric came from sulfate, and sulfate is SO4 2 minus, and barium chloride. So barium is a group 2 element, and chlorine is a group 17 element. So barium has a charge of 2 plus, chlorine has a charge of 1 minus. So we got barium chloride. So that's barium 2 plus, chlorine is 1 minus. To write the equation, or to write the formula, sulfuric acid, hydrogen with the sulfate is H2SO4 plus barium chloride is going to be BaCl2. So the formulas for sulfuric acid and barium chloride, H2SO4, BaCl2. You look on the solubility chart to find out if they're soluble. Now, it turns out that nearly all acids are soluble in water. So on the ion chart itself, it turns out you don't find hydrogen because hydrogen is a group 1 element, and those all say aqueous. So acids are aqueous. The barium chloride, we have barium and chloride, that says aqueous. And what you predict is that the hydrogen goes with the chlorine and the barium would go with the sulfate. So the reaction would be that you get HCl plus BaSO4. Because hydrogen has a charge of 1 and chlorine has a charge of 1, it's just HCl, and barium has a charge of 2 and sulfate has a charge of 2, BaSO4. Well, HCl is aqueous. Everything that's in group 1 is aqueous. But the question is, what about this barium sulfate, BaSO4? When you look on the this chart, you have barium, and you go over to sulfate. Barium sulfate is a solid. So the barium and sulfate says S, so that is a solid. That's a precipitate that forms. So when you want to make a new compound, like you want to make barium sulfate, you can take sulfuric acid and react with barium chloride, and you get barium sulfate, which is a solid. And you also get hydrochloric acid. This equation is not balanced. To balance it, you'd put a 2 in front of the HCl. And that we have 2 hydrogens and 2 chlorines on both sides, 1 barium and 1 sulfate. Sometimes no reaction forms. And how you tell if no reaction forms is if both of the products are aqueous. I don't know if I have an example here. It's really not such a big deal. What's important is that you can identify which of the products is the solid, and that's just as simple as when you figure out what the products are going to be, you look on the solubility chart and like iron hydroxide says solid. Or if you want to know something that is not going to dissolve in water, you can just look anywhere for an S. So like here, like cobalt phosphate must be a solid. Or you look here, this AQ is magnesium sulfate. Magnesium sulfate forms a solution. All right, so the determining solubility assignment, you want to have the solubility chart handy. And if you have the solubility chart handy, then you'll have no trouble with that. But that's the thing you want to practice with now is using the solubility chart to try to get things figured out. So the solubility chart, I mentioned this, it's on the back of the ion chart if you have that paper, or right here in the folder for this week in Unit 6, week of 2.1 to 2.5, the solubility chart has there's some other notes at the top that are some generalizations, but usually you're just looking at the meat, the guts of the chart itself. Let's see, I forget what's at the top. Yeah, so whether things are aqueous, it depends upon the portion of it that's aqueous. Another thing that you'll see in the chart is D. So if it says D, that means that that compound really doesn't form, or that it decomposes. In other words, it decomposes into the elements that make it up. For instance, aluminum sulfide, the aluminum and the sulfur. Aluminum sulfide isn't really a compound. Instead, you have solid aluminum and solid sulfur as separate elements. Those are non-reactive with each other. It doesn't form a solution. Neither solid aluminum nor solid sulfur are soluble in water. So you're not going to get ions of aluminum or sulfur, or you end up with not really anything. So the D's aren't really going to be an issue for us. Same with the things that are dashes. Those are also compounds that don't form. What you really care about are things that say S and AQ. So anyway, in the thing you can do today, this determining solubility assignment, is just so simple as using the solubility chart to predict which products of reactions are soluble or not. So for instance, I mean this one, and they're in random order and whatnot. So what are the states of these things? So sodium chloride, silver chloride, copper sulfide, zinc hydroxide. You look at the position on the ion chart. If you think that copper sulfide is aqueous, you can drag an aqueous to there. So that's like a matching one. And then other ones, which anion would calcium bond with the former precipitate? So calcium 2, which of these forms a solid? So on the ion chart, or on the solubility chart, you look for calcium, you go across, look to see is it sulfide, hydroxide, chloride, or nitride, and so on and so forth. So you shouldn't have too much trouble with that. All right. I know that was kind of a bunch of stuff, but that's the way the solubility chart works. It's kind of simple. It's another tool that you got to have handy. So like the periodic table is very important. You can always use that. That's a very useful tool. The ion chart is a very important and useful tool. The solubility chart is now an important and useful tool. Those are references that chemists use all the time to figure out like what's going to happen in a reaction, if anything at all, what the names and formulas for compounds are going to be. You don't have to memorize any of it. It's just a thing you just gotta know. Some chemistry teachers make you memorize the solubility chart. That's kind of a waste of time if you have reference to it all the time. But if you use it enough, you end up just kind of learning it. You just kind of know what's going on. But I don't expect you to have it memorized. All right. So, what kind of questions do you have about the lab or anything? If you don't have any questions at all, you don't have to stay in the Zoom. I got you marked down for attendance and all that. We'll see you back in class tomorrow. But if you've got questions about the lab or problems or anything else, you can put them in the chat, turn on your mic, just ask. Okay, well, if you don't have any questions, I'll see you tomorrow. You can always ask questions in class. You can send me a message in Schoology. I'll stay here for a while if you have questions.